So, Dijkstra's algorithm. Dijkstra's algorithm makes a very important observation on top of the ith closest vertex algorithm. And here's the observation. You know how in the ith closest vertex algorithm we constantly recalculate the distance for these vertices outside of x? Well, Dijkstra's algorithm says, why do we have to constantly recalculate those values? Why can't we calculate those values once and just recalculate the values that would change when we add a new element to x? So I'll show you what that means through an example. Let's start off with x as, x right here. This is x. And so how far away are the other vertices? Well, all that really matters is how far away are the vertices that have edges coming out of x, right? Have edges coming out of this vertex, right? So how far away are these vertices? Well, this is 9 far away. This is 6 far away. This is 13 far away, right? So we just mark these with a distance that we know that we could get at least a path that is maximum this value to each of these nodes. Okay? So we get this path, and now we need to add a vertex to x. And of course, we find the minimum distance vertex. And we simply say, add this vertex to x. Okay? Easy enough. Now that we've added this vertex to x, what does this mean? Is the minimum path to here going to change by adding this vertex to x? No, no. This vertex is not connected at all to this. So whatever we calculated for this minimum path stays the same, right? The only distance measurements that will change are for those vertices that might change, are for those vertices that are adjacent to the vertex we just added to x. Make sense? So if we look at just those edges and recalculate the distance to these vertices, we now could compute a new distance prime. Okay, we don't change the value here because the distance using this node is 6 plus 14, which is greater than the distance to this node that we've already established as 13. And this doesn't change because it's not connected to 6. But these two that had originally infinite distance, now we get a maximum path distance of 24, 18 plus 6, and a maximum path distance of 36. 30 plus 6. Okay? And now, in order to find the next vertex that should be added to x, what do? I just find the minimum value of v minus x. And in this case, that's this node right here. Okay? And again, we add this node to x, and what do we recalculate? We look at this edge. We only look at the edge that's coming out of the node that was already added to x. That's the only thing we really need to look at. And we look at this edge and we say, okay, if we use this edge, then the distance to this node here is 9 plus 10, which is 19, which is less than the path that we had calculated before of 24. So we change the distance to this node we change the distance of this node to 19. And now again, we want to add a path to x. Then we choose the smallest value, which is 13. We add it to x. We only look at the edges that are coming out of this node, and then we recalculate. 20 plus 13, 33. That's less than the 36 it was before, so we change this value. And 13 plus 25, which is 38. That's less than infinity, which was the previous value, so we readjust it. And then we go on continuously until slowly x engulfs the entire graph, and we've calculated the shortest path from S to any other vertex in the graph. Okay, so the main work that we were trying to minimize was calculating that d prime in every iteration. But d prime only changes when the node v that is adjacent to d prime is added to x on iteration y. It shouldn't change otherwise. So we should only calculate that d prime then when you add in that node. So the new algorithm looks like you have n iterations of a for loop, and then you find the minimum vertex that's in v minus x, and then you add it to x, and then you update d prime for each u that is adjacent to v. For each u that is adjacent to v. Okay, so what is the running time for this algorithm now? Well, what do we know? We know we go through this work. We go through this work m times, right? We look at each edge once. Why do we look at each edge once? It's because for every node that gets added to x, we only look at the outgoing edges of that node. That's the only time we look at the edge. So we only look at an edge when the vertex that is its beginning point gets added to x. And therefore, this right here only happens m times. Now is the problem. We have n iterations here, and we need to calculate the minimum. And how do we calculate the minimum of an unsorted list of nodes? How long does that take? I mean, it takes linear time, right? It's just a brute force process. So we've eliminated this mn term here. We've made it much faster, but we've still got this n squared term, which we need to address. And the lucky thing is that we can address it using advanced data structures, as we'll see in the next lecture part.